Hello, welcome to a lesson for Module 7, Polymers and Chemistry of the Earth. Do I have to repeat myself 10,000 times? Polymers have many repeated units. So let's start off by talking about polymers, and here's a picture of me, and of course the first thing that will knock you away is how handsome I am. At least that's the only thing you'll say to get a good grade though, right? And actually most of what you see on me and there is a polymer. There's two exceptions. My eyes, top layer, well, it's tears and then stem cells, and the surface of cells are they're phospholipid bilayers. They're not polymers. And teeth. Your teeth has the surface of that is a mineral hydroxyapatite. Everything else, hair, skin, and fingernails, you can't see my fingernails, they're all made of a protein, which is a polymer called keratin. And my clothing is cotton, which is a polymer of glucose. So polymers, what are polymers? They're very large molecules, huge molecules. A little bit of logic here. All plastics are polymers, but not all polymers are plastics. So what's a plastic? A plastic is something that can be molded when it's molten. So diamond and a protein, starches, these are all polymers, but they're not plastics. You can't melt down a diamond and then mold it into something. And the smaller units of a polymer are called monomers. Let's start with the simplest kind, addition polymers. It means one atom is added to one molecule is added with no loss of atoms. So polyethylene is the largest, and polyethylene, my MacBook here that I'm recording this on, this is polyethylene. Most of the plastics you see are polyethylene. And there are other addition polymers that are substitute polyethylene. So here, take ethylene, that's the stuff that makes bananas ripen quickly and all fruits, and then it's added to form this really long alkane, and that's polyethylene. And there's two types, high density and low density. High density is straight chain. It's my computer here is made, the shell of it is made by high density. Low density is the wimpier kind. This is used to make plastic bags and these types of things. And the high density is straight chain, low density is the branched form of that. Let's talk about the different types of addition polymers. We talked about polyethylene already. Polypropylene, these are things like bottles and luggage can make a polypropylene. Polystyrene, styrofoam. PVC, polyvinyl chloride, these are things like records and some tiles on the floor are PVC. Polyvinyl chloride, also known as saran wrap, they have that for food coverings. Teflon, this is just like polyethylene but has fluorine instead of hydrogen, and that's like the non-stick coating. It's really inert, really great compound. Polyacrylonitrile, this is things like yarns, wigs, and some paints have this stuff, and if you notice it has a cyanide group in it, so be careful if you decide to burn that stuff. Polyvinyl acetate, this is stuff for adhesives, chewing gums, these types of things. And polymethyl methacrylate, so I think of acrylic nails and any of that, so it's also used for bowling balls and these types of things. So plastic properties. So plastic, we told you before, means it can mold it. And there's a couple ways you can do it. Compression molding. So you take a powder and you heat it, and then you apply to it, and you get a polymer forming in the cavity. Injection. You take it and you melt it and you force into a plunger and you inject it into the mold. Extrusion. You take and you put it through a something that extrudes out. If you ever seen spaghetti being made in like the Play-Doh, where you take Play-Doh and you push something down and these little spaghetti things come out, that's what extrusion is. That's how they make tubes. Tubes are extruded. That's the difference between pipe and a tube. A tube is extruded and a pipe is welded. The way you make a pipe is you take a piece like your pipe in your toilet paper. That's cardboard pipe. Well, they call it tube, but it's really a pipe because if you see it, it's kind of wrapped around. That's how you make a pipe. You take a piece of steel and you wrap it and you weld it that way. A tube is extruded. And blow molding, this is how a lot of bottles are made. You take a molten plastic and you blow into it and it fills a space into the mold. That's blow molding. And elastomers, this is a type of polymer that return to their original shape after stretch. So rubber bands, and this is how rubber bands work and rubber in general. You have these two like molecules here that are kind of jagged, and you have sulfur bonds between them. And what happens when you pull on these, these molecules, these here, will straighten out, and then when you let go, it will reform its original shape. And vulcanization, they take rubber, natural rubber, and they add sulfur to it to vulcanize it to make the rubber stronger. Hair has a similar property. Hair has disulfide bonds in the cysteine amino acid groups, and so this gives hair some of its elastic ability as well. Polymers and paints. So paint. There's some chemistry behind painting. So right, you paint your walls and then you let it dry, and then you have plastic in your wall. So there are three parts: solvent, binder, and pigment. The solvent, typically water, can be other types like oil-based. Binder, this is the monomer, and so and the pigment is the color. So what happens when the solvent evaporates, the binders polymerize, and you get some sort of plastic encoded pigment on the wall. And even notice you can peel paint off sometimes. It's just like a little rubbery layer of plastic. Now we talked about addition polymers. Now let's talk about condensation polymers. These are polymers that add a molecule when they come out. And it's usually water. It's condensation polymers, so it's usually water. And proteins. Proteins are condensation polymers as well. Protein is a polyamide. Nylon is a polyamide too. And when they form, water pops off. Likewise, for proteins, when we digest them, water is added to the protein. And PET, polyethylene terephthalate, also seen PETE. This is a polyester, kind of like Austin Powers in his polyester suit. This is a polyester, meaning many esters, polyester, many esters, and PET has this ester linkage there. So next time you drink a soda bottle, think of polyester. And also phenylformaldehyde resin. This was known as Bakelite. So this is the first synthetic polymer, and Leo Bakelite did this. And polycarbonate is another condensation polymer. These are tough. These are used like in glasses, safety glasses and eyeglasses. A lot of times are polycarb, helmets, and these types of things. These are polycarbonates. Polyurethane, this is kind of similar to nylon. When I think of polyurethane, I think of furniture finish. So polyurethane have I've painted furniture before with polyurethane before to make it a little shinier and tougher. And epoxy resins, these are interesting. So I've used epoxy. Well, a lot of dental fillings now, they used to be mercury amalgams. Now they use epoxy resins. You take sand basically and you mix it with epoxide, and then these react and they polymerize, and that makes it tough. I had trouble with my rear view mirror on my car falling off. I finally got frustrated after buying the kit. I went and I got some really strong epoxy, and I stuck that thing on there with a really strong epoxy resin, and I think I'd have to break the window in my car to get the mirror off now, which I'm actually quite pleased about that. So epoxy resins can be very powerful. So silicones. When you think of silicones, you might think the first thing is breast implants. And breast implants for a long time were silicones. Then they stopped using them because they thought they were cancer causing, and now we're going back to using them. What silicones are, they're these molecules here. If you see here, oxygen silicone, and then they have the alkyl groups attached to it. These are these kind of oily kind of things. Synthetic oil for uses in engines, they use this stuff. Why do you use it? Well, it's water repellent, heat resistive, and resistant to chemical attack. So silicon oils, that would be nice, resistant to chemical attack. It would be nice to use in an engine. So synthetic oils tend to perform a little bit better than plain old motor oil. And silicon rubber, so if you make these longer chains, so oil is going to have the shorter chains, longer chains going to be solids, That's like the caulking seal around bathtubs and that stuff, and also fake body parts like ears and noses, and a lot of Halloween masks are made from silicones, and some breast implants. So this is what those are used for. So how do we get rid of polymers? Polymers are designed to be very chemically inert. And that's a great thing, and that's what we use them for. The problem is they don't decompose well. So burying them, they're going to be around for a long time. What can we do? We can incinerate them, we can burn them, get electricity. The problem is you form harmful gases. You can scrub the flue gases. That's one option you can do for that to mitigate that problem. Also, you can recycle polymers. And the thing is that when you recycle them, they turn into lower value products. So the polyethylene that's used to make my MacBook here is pretty high value product here. That's the problem is that after something else, you use lower products. So things like garbage cans. Garbage can is an example of a low value product. A MacBook computer is an example of a high value product, right? Because a MacBook is a lot more expensive. So you can use cheaper things like timber, artificial timber, or other types of things. Other problems, plasticizer, and this is things that are debated right now. In fact, I just read an article by the American Chemical Society talking about plasticizers and how we don't know about the toxicity. They seem to be low toxicity. We find them everywhere. They're all over the place, and it makes us a little worried. The other thing is that polymers are made from petroleum. Petroleum is a source of polymers. What do we do as petroleum reserves deplete? We have to find something new. Now, here's a picture of the Earth, and we're going to talk about the chemistry of the Earth. And although I'm going to talk a little bit, you've maybe taken a geology class. I have a different viewpoint. We're going to use the geology terms, but I'm going to talk about the chemistry terms as well. And looking at the Earth, you notice something. You see the continents and you see the ocean. So let's talk about the Earth. The Earth is extremely temperate. Compared to the other systems and other heavenly bodies, the Earth is strangely temperate. And also, the Earth has a lot of liquid. The only other body that we can say for absolute certain that has liquid on the surface is Titan, a moon of Saturn. And there is some liquid on the surface there. But the Earth has a lot of liquid. There's a lot of life. As far as we can tell, this is the only place life exists. And the Earth has a very reactive atmosphere, which is also very strange. Because the plant life, primarily algae, puts the oxygen in there. The Earth also has a molten core, unlike Mars or the Moon that do not have molten cores. So what's the Earth made of? The Earth is roughly spherical, the diameter about 13,000 kilometers. That's about 8,000 miles, if you're wondering. What's the Earth? The core is mostly iron. We don't know if it's straight iron or has some nickel in there, so it's not entirely known. The inner core is solid, the outer core is liquid. There's also a mantle of the Earth. The mantle is a slurry, it's a rock slurry. It's like cake batter. You're seeing cake batter, that's a slurry. So it's like this rock kind of slurry. And then the crust is very thin on the top. And what is the Earth's surface made of? So the Earth is mostly made of iron. Iron is if you were to pick one thing the Earth is made of, you would say it's made of iron. The iron, it's dense. It has gone towards the center of the planet, and then the lighter kind of stuff, the silicates, float on the surface of this molten iron, and that's the crust. The crust is the silicates, and that's what you can see. Most of the what's on the crust of the Earth are silicates, silicon and oxygen. And there's other stuff too, but there's quite a bit of silicon, oxygen, and quite a bit of water too. And plate tectonics, this is not written in your books, but I thought I'd include plate tectonics. This is the theory about how plates have formed. And this accounts for things. So the plates, mountains form. You can have volcanic mountains, like we have volcanic mountains here, but two plates can go up against each other, and then mountains can form from that. You can also have subduction zones where one plate goes under the other. But in both this case and these cases where the plates slide up against each other, you can get earthquakes where they get stuck, and then suddenly they'll move, and that causes the earthquake. You can have ones going down. This can create earthquakes that way. And also, as this plate is going down, it creates currents which can make volcanoes alongside here. So as this is going down, it can create currents that create volcanoes there. So this explains a lot. And also another explanation for volcanoes are hot spots. Hawaii is believed to be formed from a hot spot. There is some debate in the community on this, but I'm going to go with what the current accepted idea is, that Hawaii is formed from a hot spot. And I'm going to talk about the rock cycle, and I'm going to start with igneous rock. So igneous rock is made from magma, and there's extrusive and intrusive. Extrusive is when rock that reaches the surface cools rapidly, and the intrusive, it cools slowly. So the extrusive, these tend to be denser, and they tend to have more of a randomized pattern. The intrusive, they tend to be more crystalline. So things like quartz, really pretty quartz crystals tend to happen in intrusive rock, and then the kind of the basalt, these types of rougher type of materials, the glassy stuff tends to be more extrusive type things. So sedimentary rocks, there are a few types. Detrital, you take smaller particles, erode, and these compress over time to form larger rocks. These form from small particles, and these accumulate to form new rocks. So sandstone and shale are example of these types of things. There can also be chemical sedimentary rock. These are precipitation and other things from coral. Coral, for instance, precipitates calcium carbonate. And these types of things, these precipitate over time. That's because we have our ocean. Precipitate is when a solid forms from a chemical process in a liquid. So we have sedimentary rock. We have igneous rock that's made from magma and lavas. We have sedimentary rock that is made from smaller rocks pressed together. Now we have metamorphic rock. So the metamorphic rock is when sedimentary rock or igneous rock is further changed by heat and pressure. So these are going to go chemical changes by heat and pressure. And let's talk about definitions, rocks and minerals. Minerals are elements or compounds. So these are pure substances that are crystalline and have definite restricted composition. Rocks are combination of minerals. So if you say this is a mineral, you're saying this is a pure compound or element. And if you say this is a rock, this rock has one or more minerals in it. So mineral is much more specific than a rock is. Inorganic solids, these are rocks and minerals. Organic, these are from decayed remains of plants and animals. So let's talk about the common ones. Silicates, these are really important. These are found in very high concentrations in the crust of the earth. The general chemical structure is SiO4. This is where I disagree with the geology on this. I think that it's SiO2. So the chemistry definition is SiO2, the geology definition is SiO4. It's because one silicon atom is surrounded by 4 oxygen atoms. But if you count each one up, there are 2 oxygen atoms for every 1 silicon. But I'm going to go with the geologists and let them win this argument. And there's different types of patterns, and you can create a crystalline solid. And there's different types. So silica in general is hard, durable mineral. A lot of sand. The sand here in Hawaii is actually carbonate sand, but the sand in most other places is silica sand. Quartz, this is a crystalline solid, and it has a 3-dimensional lattice. So this goes in 3 dimensions, this silicon. Now, we can have long chains or fibrous chains. So these chains of magnesium and calcium silicates, that's also known as asbestos. And asbestos is a natural mineral. And these are great. They're strong, flexible, they don't corrode, and they're great for thermal insulation. Problem with them, and they're going out of style, is because of lung cancer, specifically mesothelioma, these types of things. So there's a link between lung cancer and smoking. There's a synergism. So a synergism means that they amplify each other. I have a couple, but two of my nephews. One nephew when he's by himself, he's a good boy, and the other nephew when he's by himself, he's a pretty good boy too. But when you get those two together, they're a bunch of holy terrors. Okay, so that's just like asbestos and smoking. My 2 nephews, when they get together, they wreak havoc. There's a synergism between them, just like asbestos and smoking. And mica is another silicate, but it's found in sheets, so rather than long fibers. So what do we use minerals for? Let's start out talking about pottery, and this is old technique. You take clays, and then you heat them up, and you get pottery. And also you can make glass. So silica, and now I'm using the chemistry definition rather than the geology, SiO2. You mix calcium carbonate and sodium carbonate. So you mix these two together, and this lowers the melting point to about 700 degrees Celsius, so that way you can melt these things and make glass. And that's how you make silica glass. But there's other types of glass. So soda lime glass, sodium and calcium silicates, this is ordinary glass. So this is, we talked about the Egyptians figured this out. Borosilicate glass, use boron oxide. This is heat resistant glass. So this is Pyrex. This is what I make. I have my beakers made out of in the lab. And also a lot of oven glasses are made of Pyrex. Aluminosilicate glass. This is more highly heat resistive stuff. Lead glass, also called crystal. This just you have lead oxide in there, and it looks pretty. Color glass, different compounds have different colors. This is for like stained glass windows. Photochromic glass, you can use silver chloride or bromide. This is to make those lenses that turn dark in the sun. So when the glasses that turn dark in the sun, they're made from silver chloride. It just turns silver metal in the glass. Laser glass, neodymium. I used to work with lasers, and so they're purple rods. They're about this long. They're a couple inches long, and they're really expensive. I mean, one of these purple rods about 3 inches long. That'll cost about $5,000. So they're really expensive, and they have a little bit of neodymium. Typically neodymium YAG, yttrium, aluminum, garnet. Those are used for lasers. And frosted glass, you just take normal glass, you etch it with hydrofluoric acid. This gives it a frosted kind of surface. If you ever go to Iolani Palace here in Honolulu and look at the glass there in the front of the palace, that has frosted glass. That's made by etching with hydrofluoric acid. Also in my school, Honolulu Community College, there is a kind of a glass artistic thing of the hokulea. That's made by frosted glass. That's how they make it, is they etch it with hydrofluoric acid. And ores, I'm talking about ores and metals. So ore is a mineral that has a lot of metal. And the ore, there's a few times that you find just the plain old metals, but this is rare, and they're the ones that are really expensive. So gold and platinum, for instance, you can find gold and platinum in its pure form in nature. There are very few that you can, but you can find gold and platinum in their pure form. But most other ores you find as oxides, sulfides, carbonates, these types of things. And so we need to get the metals out of the ores, and so we do it by chemical process. I'll show you the common one with the blast furnace. So here are some important ores here. So some important ores here. So for instance, chromium, you can get it from iron dichromate. This is where you get chrome from for resistive coatings. Gold, you just find it as is. Lead, find it as lead sulfide. You can find these for lead soldering and batteries is what it's primarily used for. Magnesium, used in wheels, luggage. So magnesium, interesting metal. Mercury, find it as cinnabar. It's this red kind of stuff. Uses for thermometers and barometers. They have mercury for other usages, so use it in fluorescent lights, for instance. So these are not the only uses. Nickel, found in nickel sulfide, used for coins. Coins are nickel-plated copper, and also some stainless steels. Platinum, it's found as is, really expensive. Silver, you can find it as is, but you can also find a silver sulfide. Found for jewelry, electrical kind of stuff. Sodium, find a sodium chloride. It can be used as a heat transfer medium reducing agent. Tin, like tin oxide here. This is corrosive resistance. So tin cans, maybe you heard tin can before. A lot of times it's steel cans coated with tin. Tungsten is used for light bulb filaments, for instance. Uranium used for energy source, and we've also been using them for weapons for depleted uranium. And zinc used as for a coating. Iron, we use iron quite a bit. And iron, the typical ores are hematite and magnetite. So magnetite, actually, Fe3O4, this is another thing where the chemists and the geologists fight. Magnetite is Fe2O3 and FeO, so they, rather than saying that, they just combine the two to say Fe3O4. That's not really the chemical compound, but that's the geologist's misinterpretation of the chemistry. Now, how do you get iron out of it? You take it and reduce it with carbon. I'll show you that in the next slide. Pure iron, it's pretty strong, but it's relatively soft. If you hit it with 2% carbon, that's called structural steel or carbon steel. And that's what when you see iron, you primarily see it as steel and not really iron. And high carbide steel, this is very hard but brittle. This is about 10% carbon. It's also darker. It's like it's made of horseshoes. Horseshoes are made out of this. And actually, the people that figured out how to use this technology really well are the Japanese. The Japanese made samurai swords, and samurai swords are sharp on one end, and they're made from carbon steel, but they put little ribs. If you look at a samurai sword, there's little ribs of these dark things. That's iron carbide. So the iron carbide act almost like ribs in it and make the swords very durable. There's also stainless steels. Different types of stainless steels have different metals in them. So a very common one is 304 stainless steel. That's a very common one. 316 stainless steel, that's used for food and drugs. So if you go to mixing tanks in food manufacturing plants, they're going to be made from 316 stainless steel. And just the different numbers, they correspond to different. There's no rhyme or reason what the numbers mean. They just, if you look it up in a book, they tell you what metals are found in what concentration. So this is how we make most metals, is by a blast furnace. You put in the top the ore, limestone, and coke. Coke is carbon. It's a purified form of carbon. It's not Coca-Cola. And you put this in here, and then it's called a blast furnace because air is blasted into here. And then what happens is that the carbon reduces. So it reduces, remember, it rips oxygen out of the ore, and then the carbon dioxide comes out the top, and then on the bottom there's the molten stuff. There's the molten iron on the bottom, and the top, floating on the top, is slag. So slag contains the impurities, typically the calcium and magnesium silicates are what make a slag, and the slag, they just float off, they just draw it on out. And then off the bottom is the molten iron, and they have it down and they make it to form bars or steel. So if you've heard of pig iron before, that's actually a farmer's metaphor. That came from the Industrial Revolution. People were drawn from the farms to the cities, the industrial centers, and the farmers thought that these iron bars being formed looked a little bit like a bunch of baby pigs suckling on the mama pig. So hence the name pig iron came from. So that's just a farmer's metaphor left over from the Industrial Revolution, if you hear that. But this pig iron is then either sold or in-house made to form other types of steel. Aluminum is not made the same way. You take aluminum ore and bauxite. Aluminum ore is typically aluminum oxide, also known as sapphire. And we talked about this before. Sapphires, it's aluminum oxide with trace impurities. Those are crystalline structures. So aluminum actually is expensive to extract from its ore. So it's really, really good idea to recycle aluminums. Metals in general, especially aluminum, are great to recycle. Plastics and glass, you do not, when you recycle plastics, you get kind of a low value product. Recycling glass, it takes a lot of energy to do that. Also to recycle plastics, it's debatable whether or not that recycling glass or plastics is really at all useful. Recycling metals, though, is extremely useful. Recycling metals is a great idea. We should do it as much as we can. And the process to get aluminum is actually electrical. You take aluminum ore and bauxite, and you melt it, but then you put carbon rods, and you have a big source of electricity, and then it will rip the oxide off of the sapphire to form carbon dioxide, and then you will get aluminum metal, liquid aluminum, and then that is then used to make whatever it is you're making.